Hi, everybody. This is Mr. Foley, and welcome to podcast 1.2. Talk a little bit about density, very little. States of matter, mixtures, and I think that's it. So let's take a peeky weeky. All right. Physical changes. A physical change is a change in mass, shape, but not identity. So if this is a hunk of clay, and it is, and I change its shape, oh, look, it is a strong young man. No, it would be nice. And here's another strong young man, but a different color if you paint it or whatever. It's still not changing the identity. It's still a piece of clay when you cut it on. If you cut something, boil something, melt something, freeze something, or mold meaning sculpt it, then it's a physical change because it's still the same thing. So the most important thing in a physical change, it's still the same thing afterwards. A chemical change changes the identity after the change. It will have a new formula. So if something burns, or dies, or precipitates, or forms a gas, now, if it changes a color, that's also usually a good sign of a chemical change because you have new properties from there. Boiling forms a gas, but it is not a chemical change. This is the evil one. Ah, evil! Much like Freddy Krueger is the evil one. 1, 2, Freddy's coming. So a chemical change changes the identity. And a physical change, remember what that changes? It changes just its physical properties. Pure substances. Elements and compounds are both pure substances. Here's type number 1. Here's type number 2. Elements are one type of atom. Now, one type of atom can be diatomic, and those are honko breath. Now, what I mean by this is the elements hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine all come, when they're elements by themselves, come in pairs. Okay, so they're always stuck together, like bicycles always have two wheels. These are the ones that are always your twos, okay, when they're by themselves. Okay. Compounds have more than one type of atom, and they do not have a combination of properties. They have new properties. So what this means, hydrogen explodes, bam, wow, when you put a flame to it. Oxygen burns, it burns. Water puts out a fire. Oh, that's lame. So that's totally new property. Ah, little sodium fun here. Sodium, it will react with your hand and like burns. It will chemically burn through your body. So if I ate sodium, it will chemically dissolve your mouth. Oops, that's you. Chlorine is a poisonous gas that dissolves your lung. This is maybe more than one. But together, sodium is yummy. Salty sodium chloride. Oh, come on. Mixtures. Now, in any state is possible. So basically, you can put any two things together and do this. Now, a mixture, by the way, is a blend of properties. That's so you can tell the difference. So a homogeneous mixture is called a solution, and every sample is the same. A heterogeneous, the samples are different. Living things are typically heterogeneous. Okay, salt water, every sample is the same. It would be homogeneous. A salad, you can see the different parts, so it's heterogeneous. Grass is a living thing, so you call that heterogeneous. 18 karat gold, another type of homogeneous, is called an alloy. Get back here. An alloy is a homogeneous mixture of metals. Now, the genius is relative, meaning if you look at grass with the naked eye, you could say it's homogeneous grass. Or if you look at it with a microscope, you go, oh, there's the mitochondria. It's the powerhouse of the cell. This is a pure element. This is a mixture, so I can divide it. Get back here. This is a heterogeneous mixture because it has layers, a top layer and a bottom layer. The mixtures are not the same. This one is tough. Basically, everything that's a mixture is going to be a heterogeneous mixture at this level. because if you count these out, look, this only has half of a big one and a little one. It's got a whole big one and two little ones. So heterogeneous mixtures are what most mixtures would be. This is a pure compound. This is a pure element. Now, the reason why this is a compound is see how these are touching? That makes it a compound. Now, these things are touching, but it's not a compound. It's an element because it's a homogeneous mixture of these two things together. Okay? And you can look at the rest if you want to, but I'll save you a little time. How to measure. All instruments have a numbered measurement, an unnumbered measurement, and an estimation. So if I put this mark right here, this would be 4.4, right? 4.4, 1. I need one more estimation. Okay. Numbered, 4. Unnumbered, this 0.4, and then the estimation. It's just passed. On this one, the numbered one would be, it's the 15 part. Then this is 16, 17, 18. This is 18. Points right smack dab on it, 0. Now on this number is estimated. This last digit is estimated. So digital devices do estimate it for you. Way back when, in like the 1970s, this last digit would flicker. And it flickered to show that it was estimated. And what happened was people would go, hey, my balance is busted. The digit keeps flickering. Instead of realizing that it flickers, 0.6, 0.7, 0.6, 0.7, 0.6, 0.7. It's an estimation in between that. So they instead got rid of the flicker because people were too dumb to know that they were supposed to. Separation by distillation. So what happens with distillation is you have a mixture and you heat it. One part boils. Other parts don't. So things have different boiling points. So if you heat it up, one thing is going to boil, and then you'll recondense it. And you can do that if you've got a mixture of 3 things. You slowly heat it up, and when the temperature is the same, it'll boil. And you keep it at that temperature till it's all out. And it's called distillation. Density is love. Now, why do I say that? Well, density equals M over V. Oh, look, it's a heart. Oh, it's love with a knife through it. Ouch. So density is mass over volume. And the units for density, your mass unit over your volume. So it could be kilograms per milliliter, or it could be grams per liter. Yeah. More dense things sink. So I don't know, if I said someone was very dense, Michael, then they would sink a lot more than someone who is much, much brighter. Like, I don't know, is anyone brighter than Michael? Ooh, was that a compliment? Can't let that happen again. So here, sediment density is 0.687 grams per centimeter cubed. Water's density is 1 gram per centimeter cubed. So Saturn is less dense, so it will float in water. Just we don't have liquid. Separation by filtration. You need to be able to draw something this. Now, you do not need to know what a retentate is, nor do you know what a permeate is, but you need to show this is what happens in filtration. So different filters will have different particle sizes, and you can filter different things. Separation by chromatography. So if I have paper chromatography, that's this one right here, it's separated by particle size, right? A big particle, if my particle is this big, I'm not going to travel very easily. And the other reason why you travel is because you're soluble. So what happens is you put a piece of paper in a beaker, and it has a certain solvent level. And this will start to get pulled up the paper, okay? So this is the solvent front, okay? The thing might be attracted to the solvent, so it travels up with it, and it might be a small molecule, whatever it is, but you'll end up with a dot. Okay. Now, every once in a while, they ask for an RF factor. There's the RF factor. I forget what RF stands for. It doesn't really matter that much. But what you basically do is you divide the distance of the top divided by the solvent front. So these are distances. And really, you should use the middle. So if you do the middle part, then you can divide that. Okay. So that's it. Oh, and then if you have the that's not a gas one. If you separation by attraction to the column and mass for column chromatography. So what happens is you've got stuff here, and then given enough time, these things will separate over time. So I've got a mixture, and it separates. And then what you do is you open this up, and then drain off just the little green boogers. And once the little green boogers are done, then you separate and pour off the little worms, and then you have left over your little purple dots. Okay. So do you see how over time this will separate? And then you just open up the burette looking thingamabobber, and it will do it. And that's called column chromatography. And review. Physical changes stays the same thing. Chemical changes change the identity. No distillation. Draw a picture. Chromatography. No picture for both. And filtration. Draw a picture. The new AP thing really wants you to draw pictures. No elements, compounds, and mixtures. By picture. Touching is a bond. And that is it. And I will say toodles.